Thanks everyone for coming out, particularly after that wonderful lunch. Everyone can hear me in the back? Okay, great. So I'm super excited to be here. I'm going to talk to you today about some of the work we've been doing in my lab on reinforcement learning for people. And I know that some of you might have went to some of the wonderful tutorials a couple days ago, but I'm going to start by assuming that there's a lot of backgrounds in the audience, and so we might have a little bit of definitional differences, and so I'm going to start with sort of some background as well.
Let me just adjust a little bit.
Thank you. So I'm really interested in the question of how do we make sequential decisions under uncertainty, which seems like a very appropriate topic for UAI. I think it's perhaps particularly given that we're in Jerusalem, or that we're in Tel Aviv and Israel, it's interesting to think about how many thousands of years people have been trying to reason about decision making under uncertainty. This quote is also in Russell and Norvig's AI, A Modern Approach, and I found it a really powerful one in which Aristotle thinks about what a doctor does. And what a doctor does is they think about the outcome they want to achieve, like having a patient being healed, and they think about the series of steps in order to do this. And they think about, if you want to get to a state of the patient being healed, what is the immediate precursor state you would need to reach in order to achieve that? And essentially do backward chaining on that sort of series of states to get back to the current state of the patient. And I think it's quite remarkable that about 2,000 years after Aristotle made this comment, Newell and Simon, who are some amazing AI researchers from CMU, realized this system in about the 1970s. So this is something people have been thinking about for a very long time. Of course, in general, that issue of just going from thinking about how do we plan to make series of decisions, we would actually like to think about how to learn to make series of decisions in quite the same way as an infant does. We think about sort of an infant learning to make decisions in the world by exploring the world and learning the effect of their actions. And that was sort of codified in the form of reinforcement learning really in the 1980s. So in the 1980s, people started to thinking about these closed loop systems where an agent, maybe a computer, maybe a robot, is learning to interact with their environment and learning to make a good sequence of decisions. And I think it's really in the last 10 years that we've seen a completely new era of reinforcement learning. I remember when I started in the field, there'd be maybe 30 people in a talk. Now at ICML, there was 150 people just in the theoretical RL section. It's a completely new world for reinforcement learning, and I think a lot of that is due to some of the phenomenal work that's been done by some of my colleagues, thinking about things like, the revolutionary advances for Go, as well as in robotics. And in particular, I think this is a beautiful illustration of sort of the huge combinatorial branching factors that occur when we think about solving a game like Go. And this has really been an enormous pivotal achievement of AI. But when I talk to people that are outside of the field, many people have heard about these results, and so they often ask me something like, is reinforcement learning solved? Often also, is AI solved, given the phenomenal results we've seen in Go and in Atari games. And I think for me to think about why that I think we're still quite far from solving AI and reinforcement learning, it's helpful to think about a parallel legacy in parallel to the work that's been going on to try to create sort of artificial humans or robots that can reason or do the same sorts of decisions as what people do. I think we've seen a parallel legacy of thinking about reinforcement learning to benefit people. So from the very early days of people thinking about reinforcement learning and bandits, which I think we can trace back to the 1940s, we've thought about people making things like teaching machines or doing adaptive clinical trials. And so they've been thinking about how do we make sort of personalized adaptive decisions in an automated way in order to tackle some of the society's biggest problems. And I think when we do that, we start to recognize there's a number of different technical challenges that we have to face if we want to be able to realize that sort of equally compelling vision of AI. If we think about what is involved in sort of Atari playing or robotics, we typically have a simulator of the domain. In the case of video games, we have a perfect simulator of the game. We often can leverage an enormous amount of data to train. And all of that experience is typically fine to fail millions of times until our system finally works, and then we try to defeat one of the grandmaster humans at that game. If we think in contrast about creating agents that interact with people, say for education or healthcare, there's a number of important distinctions. One is that we don't yet have really good simulators of how people's physiology works, how they learn, or how they behave, which means that we often have to rely on data. But now we have the additional challenge that data is sort of costly or weighty in the sense that we don't want to fail to teach 1 million people fractions. So the issue of how do we learn very efficiently becomes pivotal in these types of domains. And I think it introduces a lot of different technical challenges. And so in particular, my lab over the last few years has focused a lot on sort of how do we understand what data is needed fundamentally to learn to make good decisions for any agent, whether sort of human or artificial, and then how do we try to, in general, minimize the amount of data that's needed to learn to make good decisions. And I think this is both a foundational part of artificial intelligence, but it also has this really important implication that if we can learn faster, meaning that we need less data to learn the right thing to do, then more people can benefit from those decisions. And so what I'm going to talk to you about today a little bit is some of the work that we've been doing along this front, in particular focusing on exploration and counterfactual reasoning. So before I do this, I'm going to do a 2-minute whirlwind tour of Markov decision processes. I'm curious who here has either taken a class or does research with MDPs. All right, most people, but not everybody, so we'll do a quick overview of the notation. So I'm going to assume that there's a state of the world going to be denoted by S, and then we can take actions in the world, and we have a policy that maps states to actions. And we're going to assume that we also get a reward signal. And we're going to define a value function as being a combination of the immediate reward plus the expected discounted sum of future rewards. And critically, we're generally going to assume that the dynamics of the world is stochastic, meaning that when we take an action in a certain state, we're going to get a distribution over next states. And for most of the talk, I'm going to assume the world is Markov, meaning that the current state is a sufficient statistic of the past, and we don't have to think about prior history in order to both model the rewards and the dynamics of the environment. Now, in these cases, we're typically going to want to find a good decision policy, and ideally the best decision policy, which means the one that maximizes the expected discounted sum of rewards. And the challenge here is that in reinforcement learning, we don't know the reward signal, and we don't know the dynamics model in advance. And so this can only be estimated through data or through direct experience. Now, I'm going to talk quite a bit about some theoretical work, and in this case, we might want to try to understand how an RL algorithm will work in general. I think empirical results are extremely important and powerful, but I also think that we want theoretical results because they allow us to understand how well an algorithm will do in any environment before we deploy it. And so that means that we need metrics for evaluating how quickly an agent is learning or how good an RL algorithm is in general. And one of those frameworks is known as probably approximately correct. It comes from supervised learning. Many of you guys have seen it or probably work with it. In terms of the definition I'm going to use for reinforcement learning, it's essentially going to count the number of time steps on which we might make a suboptimal decision. So that's what the left hand is showing. And the idea is that we want to bound this with some sort of function of the underlying MDP. So we don't want to make too many mistakes, essentially. We can think of this as counting how much data do we need in order to learn to make good decisions, as quantified by the number of time steps where we might make a bad decision. Another very common approach is to think about regret. So to think about measuring the difference between the performance of our algorithm and the best we could do if an oracle told us what was the optimal policy. And then we simply sum up the differences over time between how well our algorithm is doing and how well the best algorithm would be doing. And so both of these sort of frameworks are very common, particularly in multi-arm bandits, which is a subcase of reinforcement learning, for trying to quantify how good our algorithms are. And what we're going to be interested in this case is sort of quantifying our algorithms in terms of their performance in either the regret framework or in the PAC framework. And again, I think this is really interesting and important because if we can prove better bounds, then that means that we are provably needing less data in order to learn, which means that, again, more people can benefit from these sorts of decisions. Now, one thing you might wonder about, for those of you that are not as interested in theory, is that whether or not these bounds are important in practice. In practice, is it important to try to carefully act and explore in the world? And in particular, do we need to do this in a way that's strategic? Do we need to have agents that can think carefully about the data that they're gathering in order to more quickly learn what the right thing is to do? And to think about this, I think it's illustrative to think about some of the examples from sort of DeepMind and Atari and those other sorts of domains. So this is the game of Montezuma's Revenge. Montezuma's Revenge is one of the Atari games that's considered one of the hardest for both people and intelligent agents to play. And what you can see on the top here is DQN, Deep Q Learning, which was one of the first reinforcement learning plus function approximators that had really widespread success. This is a beautiful Nature paper from few years ago. And what you can see there is that after about 50 million actions, it's only managed to learn how to go through the first 2 levels. So it's really struggling to have an agent that learns to play this game. Whereas on the bottom is another paper also trying to tackle the same domain, where what they show here is that by using smarter exploration, by having an algorithm that is more strategically trying to figure out how to explore its world, that they can do much, much better. So this is work by Mark Bellamere et al., and you can see that they're getting through way more of the rooms. So not all of them yet, that's been done since, but you can see here that strategic exploration makes an enormous difference. So having an agent that can kind of carefully think about how it gathers data in the world can be really important here. But it's not always important. So in contrast, if you think about this example, this is another Atari game called Bank Heist. And there's 2 different algorithms here. One is the sort of smart strategic algorithm, and the other one is a standard algorithm. And the important thing to note here is they look almost identical. So it's, if you didn't look at the legend here, you'd probably say, oh, these 2 algorithms are doing kind of exactly the same on this domain. And that illustrates that while sometimes it's really important to do strategic exploration and think really carefully about, how to act in the world, that it's not always needed. And we would like to figure out when is it needed and what seems to characterize when exploration is hard, when do our agents need to think really carefully about the data they gather, and when is it not needed, and can we have algorithms that are robust in these type of scenarios. So we wanted to understand this sort of and build up for the foundations, and so we're going to think about perhaps the smallest but interesting case of this, which is tabular episodic Markov decision processes. So the idea in this scenario is that you will have an agent interacting with a person or an environment where they'll be getting states and actions and getting states, taking actions, and receiving rewards, and doing this for H time steps. And then they'll do this again with a series of episodes. So we can think of there being sort of a series of episodes where we make H decisions, the system resets, we take another H decisions. You could think of this as a tutoring system that's teaching a series of students. You could think of this as a marketing application where you're interacting with a series of Amazon customers, or you could think of this as a case of interacting with a series of patients. So what we would like to be able to do is figure out good algorithms for learning to make good decisions in this type of context. And in particular, one of the sort of a quintessential question you might want to ask is, well, let's try to find a policy that optimizes over the next H steps. So we have H interactions, let's find a good policy that works there. But another thing you might want to do is not have to think about sort of long horizon planning or sequential decision making, and instead do a banded approach. In a banded approach, we think of the actions we're taking as not influencing the next state. And so in this scenario, we just are trying to optimize the one-step decision. And sort of intuitively, you might think, well, it should just be harder to do the thing on the left. If we're trying to optimize things over the long horizon, that should just be a harder problem than if we're trying to make myopic decisions. And in fact, that was a COLT, the Conference on Learning Theory, open conjecture from last year, that the MDP setting is just fundamentally harder as H increases, in the sense that regret bounds and pack bounds are going to need to scale with the horizon on which you're making decisions. So if you want to make longer horizons, it's just going to be a harder problem to solve. So somewhat surprisingly, it turns out the answer is no. So in fact, one of our recent results illustrates that if you get rid of sort of some scaling of the value function, which was proposed in this open conjecture, that the regret, sort of how bad our algorithm is doing relative to optimal, is independent of the horizon, indicating that in a particular technical sense, longer horizon problems are not harder to solve than bandit problems in certain ways. And the reason that I bring up this particular result is that the techniques that we use to show this really sort of highlight the progress that's happened in strategic exploration and reinforcement learning. And they illustrate sort of some of the main ideas I think that have come up over the last 5 to 20 years in terms of how we can think about strategic exploration and when are problems hard to solve. So if we do no intelligent exploration, which is like that algorithm I showed you, DQN, where it only got through 2 levels of Montezuma's, in these cases, it's known that the amount of data we need to learn can scale exponentially with the horizon, or in the regret setting that you can just always make mistakes. The number of mistakes you make can grow with all the time steps. Since then, there's been a lot of progress on efficient exploration, starting out with some of the really amazing work from people like Satinder Singh and Michael Kearns and Ron Brafman and others. And what they illustrated is that by being strategic, we could do much, much better. We could do much better in terms of either the number of mistakes we make or in terms of the regret guarantees. And so since then, we've now got to the point where those questions are essentially closed in the tabular setting. There was some very nice work a couple years ago showing that there were tight upper and lower bounds for regret, and we contributed tight upper and lower bounds for the PAC setting. And the key ideas of these sorts of approaches is to be optimistic, and I'll show some illustrations of that shortly. And what some of our recent work showed as well is that we can actually have problem-dependent algorithms and analyses, meaning that we can have an algorithm that can work in any domain or any tabular domain. And if the domain turns out to be easy in certain ways that I'll quantify shortly, that it will have provably better performance. And I think this is important because I think if we want to move from these algorithms being used by grad students or highly expert researchers, then we need these algorithms to be able to adapt to domain structure so that someone doesn't need to know whether or not the domain is a bandit or an RL problem, but instead they can just deploy the algorithm, and if the world is somewhat nice, then they're not going to need so much data in terms of getting good performance, and if it's a harder domain, they'll need more. So what's kind of the main idea? The main idea is, so Q in this case is the state action value function. It's an indication of what would be the expected discounted sum of rewards if you take one action, plus from then onwards follow the optimal policy. And what we often want to do is bound the difference between that and our empirical estimate. So the first quantity is unknown. We don't know what the optimal value function is or the optimal policy. If we did, we'd be done. But we have some estimate based on a limited amount of data. And historically, what people often did initially was they tried to get an empirical estimate of the dynamics model and an empirical estimate of the reward model, and they use that to do planning. So that forms an empirical estimate of an MDP, and we can do planning. The problem with that is that those sort of bounds tend to scale directly with the horizon, the number of decisions we have to make. It turns out that we can rephrase that and use tighter concentration inequalities like Bernstein and get something which only depends on H in the lower order term. And here's the amount of data that we have, and you can see that that term is decaying much faster. And sigma here is this interesting quality, which is essentially the variance of the next state of the value function. So in particular, the way I kind of like to think about it is as following. If you're driving and you are trying to get off the next highway exit, and either you get to get off on this exit or you have to drive further. If it turns out that the next exit is like another 50 miles, then the outcome of whether you get to get off on this exit or the next exit has a huge amount of variance, because either you're going to get home quickly, or if you miss this exit, you have another 50 miles and you're going to be really delayed. So there's two very big different branching decisions, and they would have very high variance of the next state value. If, on the other hand, the next exit is only a quarter of a mile away, then if the driver in front of you or the driver doesn't let you merge in, then it doesn't matter too much. Either you're going to get off on this exit, or you're going to get off 0.25 miles later, and it's not going to make a big difference in terms of your expected amount of time to get home. So this variance of the next step outcome turns out to be super important. And in fact, this was proposed by Shai Menor's group a few years ago as being a really important quantity to think about in terms of whether or not a problem is hard to learn to make good decisions in. And what we can think of this analysis as doing is proving that that is true and showing exactly how much better it can be if that quantity is small. So the way the algorithm itself works, and this is quite similar to many of the algorithms of this flavor, is essentially we are going to maintain an empirical estimate of the dynamics and an empirical estimate of the rewards, and then we're going to construct a bonus term to be optimistic. And optimism is a pretty interesting thing in reinforcement learning. The idea is that if you're optimistic with respect to the uncertainty about the world and the parameters, Either your optimism is justified, in which case you're going to get high value, or your optimism is overly optimistic, in which case you will learn and fail, and then you will update your parameters. So I enjoy this principle because I think it's a nice illustration of why you should be optimistic instead of pessimistic. And if you haven't heard about it before, I'm happy to tell you later why being pessimistic is not valuable in this case as much as optimism is. So in this case, we're going to construct an optimistic estimate of the value function using the empirical estimates and this bonus term, which is going to keep track of the upper and lower bounds on the value function of the next time step. We can do Bellman backups with this in order to get a value function, and then we can use the resulting value function and policy to act in the world. So what does this do? This gives us an algorithm where we have a main result which shows that the hardness of solving these problems in terms of a regret bound scales in terms of problem-dependent quantities. So in particular, it depends on the sort of variance of the next state value function, as well as just what is the possible total max reward you could get in any episode. Now critically, these sort of problem-dependent quantities are unknown to the algorithm. They're just implicit to the particular domain you're in, but we're going to show that the algorithm can sort of implicitly estimate these quantities, and its performance depends on these quantities, even though it doesn't know what those are. The nice thing is that it also matches the minimax bounds for the sort of worst case scenarios. So the other existing approaches are for any possible MDP, and this is going to match those results but be better if there's actually problem structure. Now this is an advantage over some of the previous approaches, which either required more domain knowledge about what this additional structure is, or were not able to match existing sort of strong upper and lower bounds. So what does this do? This gives us some insights into when our problem's hard. It turns out that two extremes of the problem are easy. One is when something looks like a bandit. Things look like a bandit if your dynamics is highly stochastic, essentially meaning that when you take an action, it doesn't really matter what action you took. The next state distribution is always the same. So we can think of that as being an instance of a bandit structure. And in those cases, our algorithm matches in sort of some of the main terms existing bandit bounds. So it turns out that if their world really looks like a bandit, it is easier, as we know, and this algorithm will cover that. On the other hand, if things are really not stochastic, if they're exactly deterministic, the problem is also much easier. It's easy to learn in those domains. You only have to take one experience to learn what happens. And our algorithm, again, can near match the best bounds for the deterministic case. So it shows that both of these extremes are quite easy to learn in, and the hard case is in the middle. The hard case is where there's some amount of stochasticity, and depending on the action you take, sometimes very different things occur, like the highway example I gave. And in those scenarios, you need quite a lot of data and experience in order to really learn what is the right thing to do, because sometimes you have high variance in terms of the outcomes you might receive from a decision. It also answers that Colt open question I posed before, indicating that we don't necessarily have to suffer with an increase in the horizon. That sometimes in the main order terms, it's as easy to work with long horizons as short horizons. So I bring that particular example up because I think it gives us a couple important points. It illustrates how we have now closed the gap in terms of understanding exploration in some of these small settings, which is giving us a nice foundation to think about much larger problems, like the Montezuma's case, or like interacting with patients or students. And I think it also gives us insights into when is it hard to make good decisions, and what is it about the environments that mean that sometimes our algorithms work really well or they work poorly. And I think there's a lot of really exciting next steps to try to figure out how do we scale these to other types of domains we'd like to think about. The second thing I want to talk about is counterfactuals. I know this morning there was a lot of talk about causal reasoning. I'm going to talk about sort of batch reinforcement learning and counterfactuals from that perspective. And I'll start with an example of why I think this is an important problem. So about 5 years ago, I was collaborating with Zoran Popovic and a few of our students. He's up at University of Washington. And this is a game refraction. And in refraction, people learn about fractions by splitting laser beams to try to feed spaceships. And the idea is that by doing this sort of manipulation, it's a way for people to learn fractions. Fractions is something that a lot of people struggle with, and it's been played by about 500,000 students. And the question that we wanted to answer in this case is, what is the right adaptive policy to help people persist and learn more? So this might be an example of a very simple adaptive policy, which is depending on how long people took to master the previous activity, either give them the top activity or the bottom activity. In general, you could imagine all sorts of state features to describe how a student or a learner is interacting with the game, and using that information to personalize what is the next activity they do in the game in order to maximize an objective like learning or persistence. So we had this, and we had this game, and we had access to about 11,000 learner trajectories. So there's a pathway through the game and how long they persisted and how well they were doing. Where we were taking actions, essentially in this case levels or activities, in a random way. And what the goal was here is to learn a new policy in order to maximize student performance, persistence. So in this case, this is an optional learning activity. It's on the web. People drop out quickly. And what we wanted to figure out is if we could keep people engaged for longer. And it was in starting to think about this problem that I really got very interested in the issue of sort of off-policy evaluation. So in particular, I'm going to think about the case now where we're not going to get to actively explore in the world or gather our data, but instead that we have access to a data set, D, which has past trajectories that were collected by some behavior policy. I'll often call that PIB. So though in this case it was random, it could be the way that clinicians are currently treating people, but in general we're going to assume that we have some sort of past data that was collected, and we want to use that to try to make better decisions. Now, this is a really hard problem for a number of reasons, and some of you might be familiar with this, but as a refresher, this is really involving what-if reasoning, and there's a couple challenges to this. So let's think about this in the context of a healthcare example. Imagine that we have electronic medical record systems, and we see for different patients what was the series of treatments they got, as well as some measure of health state. So we have a series of 3 different patients, each receiving different sequences of interventions, each with different outcomes. And then we have a new patient who comes in, and the question is, what should we do? And so the challenge here is that we have censored data, so we can't know what would have happened if we had tried different types of sequences of interventions with one of the individuals. So Suchi Sari thinks a lot about this, Elias thinks a lot about this, a lot of people, Judea Pearl, of course. I'm particularly interested in this issue when we have a sequence of decisions. So the data is censored here, which makes it fundamentally different than supervised learning. And the other big challenge that I think is particularly important in the reinforcement learning setting is that we need generalization. So if we think about the number of different sequences of activities, or in this case, treatments, that's going to scale combinatorially with the horizon, or the number of decisions we make. And so we're going to need some way to generalize. We don't want to have to try all particular sequence of patient treatments. We're going to need some way so that we can extrapolate or interpolate in a way that we can estimate what might happen under different sequences of treatments. Now, I think that this is a really exciting time to be thinking about this type of stuff. I think over the last few years, we're seeing growing interest in both sides for people interested in causal learning, causal inference, and counterfactuals, as well as from the machine learning community. And I think that this is an amazing area that isn't just happening for the intersection of these two communities, but it's also a huge part of things like biostatistics and epidemiology and econometrics. And so I think it's a really exciting time to think about combining across these different ideas in order to really make methods that work and scale in the way that we want them to. So what would I like to do in this scenario? Well, I'm really interested in this issue of batch counterfactual policy optimization in the sequential setting. So what I would like to do is to be able to find a decision policy that we can deploy in the future and make a series of decisions in a way that we get the expected best performance. So I want to say, given our existing data, I want to extract a new policy that I think is going to do really well in the future. And so one thing you might imagine doing is you might try a whole bunch of different policies, you try to estimate in some way how good each of them are, and then you pick the one that has max. Now it turns out that even if those estimators are unbiased, this approach that I have up right now can fail. This is work led by my former student Shayan Daruti, who just recently graduated, and in this case, it turns out that even if you sort of take completely unbiased estimators, sometimes doing this, just take the max of all of these, can fail. And so we're going to need better approaches. And in particular, I think of what we've been doing over the last 5 years as sort of being this quest for structural risk minimization or cross-validation for reinforcement learning. So I think in supervised learning, if you want to figure out like a good classifier or a good regressor to use in practice, we have some really good tools for understanding what that means. We have structural risk minimization that allows us to choose across different types of linear regression versus a deep neural network. And we have practical tools like cross-validation that allow us to pick things so that when we deploy them, we have high confidence in how they might perform in the future. I think the challenge right now is that in reinforcement learning, we don't. We don't have these type of kind of off-the-shelf tools or really standard well-developed theory to try to answer these questions. And what I would like is something like the following. I would like us to be able to say, I'm going to try to find the best policy, maybe in a whole set of different types of classes of policies, such that it has a good future performance, where I can give you some guarantee on that performance or guarantee on the lower bound of that performance. And I would like that to depend on sort of how complicated the policy class might be. Maybe if I'm using a very simple threshold policy, that's going to have sort of a low complexity. If I'm using a deep neural network, it should have a high complexity. So I just don't think we have this type of thing yet, but I think it's a really exciting goal to have, and I think it would allow us to really unlock a whole bunch of applications if we could have both empirical tools like this and theoretical. So we can think about this sort of quest as involving several different components. One is in part of policy evaluation, where we try to say, for a decision policy, how good is it, given some old data? One part is policy optimization that says, which of a set of policies should I pick? And finally, we have to have an error bound, which says, how sure are we in these types of estimates? Now, I think one important question that comes up is that in reinforcement learning, it's not even clear what our hypothesis class should be. So are we thinking about looking at specific models, aka dynamics models or reward models that describe a Markov decision process? Are we thinking of using different function approximators to represent a value function? Or are we thinking directly parameterizing a decision policy? So there's a whole bunch of just even structural choices that we have to make in these cases. Let me start with just talking about the importance of methods for policy evaluation and some of our progress on that. I think policy evaluation is an important question within its own right, because in many cases you may be interacting, or I'm sometimes interacting with people that want to know for a particular decision policy how well it will do. So this might be something that a new expert is curious about, or another one that's been proposed and they want to know how good will this be before we decide to try it out. Now, there's a huge amount of literature on policy evaluation. The majority of this has focused on the one time step case, and particularly often in one binary decision. So things like treatment effect analysis is a very mature field. There's a ton of work on that. And the idea in this case is that we have some old data, and we want to figure out, is it better to give someone a pill versus give someone an injection? And can we figure out how good a decision policy might be in this setting? But what I'm really interested in is thinking about when we're making not just one decision, but a sequence. And in that case, we have a lot of challenges. So in particular, I like this figure from some of my colleagues. This is from David Sontag and Pranali Joshi-Velez's group, led by Omar Gottsman. And this illustrates some of the challenges that come up when we have sequential data. So imagine that we have a cohort of patients which have received a series of treatments. And what we want to do is figure out how good is what is the predicted performance of a particular treatment policy. So let's say our treatment policy is going to choose to do mechanical ventilation. So we had a whole bunch of people, and then now we only want to consider those that have received mechanical ventilation. So that causes us to go downwards, and now we've lost some of our cohort. Some of our patients did not receive that treatment sequence. And then next, our policy would say we want to do some level of sedation, and so again, we can only use the people that happen to have that level of sedation. And what you can see here is that as we make a sequence of decisions, we start to lose part of our population because only a subset of the patients matches the desired treatment policy. And essentially this is because different policies are going to take different actions, and that's going to lead to different state distributions. Kind of inherently, for a policy to be different, then it's going to have to end up making different decisions and reaching different state distributions. And so in this case, we may end up with a very small subset of people or a very small cohort that actually matches our desired decision policy. And so one of the things that I did with my former postdoc, Phil Thomas, is to think about how can we do sort of more data efficient policy evaluation? How can we squeeze the most we can out of the existing data and cohorts that we do have access to? And the thing that we're going to introduce here is to try to do better by being more explicitly biased. Biased in the sense of a bias-variance trade-off. So in particular, for counterfactual reasoning for policy evaluation, I think of there as being two broad camps. One is using parametric models. So we could use parametric models of the dynamics or the reward or of the value function to try to fit the data. And one of the strengths of this is that these estimates tend to have low variance, and one of the downsides is that they might have high bias. And so even with infinite amounts of data, they might give us an estimate of how good the policy is that is wrong. In contrast, we can use things like importance sampling, which try to directly correct for the state mismatch between a behavior policy that was used to collect the data and the desired target policy you're trying to evaluate. And these are nice because they give us a real unbiased estimator of how good our decision policy is, but they can have extremely high variance. And so one of the approaches from statistics is to combine these two, to do doubly robust estimators, where we combine together some of the strengths of parametric models and importance sampling. And the nice aspect of this is that we can sometimes have smaller variance than importance sampling, and it can be unbiased if either the model is realizable or the behavior policy is known. And this work was really brought over to multi-arm bandits in around 2011, and then to reinforcement learning in around 2016. But the idea that we came to was to say, well, we don't necessarily want unbiased estimators. And sometimes we really just want accurate estimators. And if the variance is really large, we may be paying sort of too large of a price to try to get to an unbiased estimator if what we really care about is mean squared error. And so in particular, we thought of how can we trade off between estimators that have high bias and low variance and estimators that have low variance and high bias. And in these cases, because we're making sequences of decisions, we can basically think of just blending between these two types of estimators by breaking a trajectory and using part of it to have an estimate from a model and part of it to have an estimate from an importance sampling. And we can think of sort of either using one step, two step, or up to H steps of either of the two models and getting this kind of weighted trade-off between bias and variance. In particular, we can sort of just directly create all of the get all of these estimators, and then use a quadratic program to try to directly solve this. So this is a way to try to directly get an estimator that is going to minimize the mean squared error. The nice thing about this is that we can still prove that both of these types of estimators we introduce are consistent. One of the key technical ideas here was how do we estimate the bias? Bias is, just as a refresher, the difference between the true value and your estimated value. If you actually know the bias, then you've solved the problem. And so we had to use a particular insight here around the confidence intervals in order to get a good estimate of the bias. So we introduced these two new estimators in order to try to get a better trade-off of bias and variance. And then we looked at the result in a number of different small simulations to try to understand what the trade-offs might be. And in particular, what you can see here, this is just for a small grid world simulation so that we can try to compare different algorithms. What you can see on the x-axis is the amount of data we have. So this is essentially the amount of our prior data set that we have. It's a log scale. And then on the y-axis, you can see mean squared error. And the green line is the doubly robust estimator that is unbiased. You can see it's doing fairly poorly here. The model, which is black, is doing well, but asymptotes, because eventually, if it has a large amount of bias, it can't continue to leverage any additional data. Importance sampling is going to continue to go down, but it can go down quite slowly. And what you can see here is that our magic algorithm is doing substantially better. So its mean squared error is just lower. But I think the important thing is not that its mean squared error is lower, but when you look at when it reaches that mean squared error. So in particular, in this case, you can see it's reaching a mean squared error that is quite small with about 1/10 the data of some of the other methods. And that's important because that means that we could use this estimator to get a good, accurate estimate with 1/10 the data of the other methods. And that means also that we could unlock some of the application areas where we're just never going to have that much data. There are some conditions where we're just never going to have that many patients, and we would like to really be able to leverage small data as well as large data in these cases. So I think this is an illustration where by doing a better sort of trade-off and getting a better statistical estimator, we really can get something that's much more data efficient by focusing on a bias variance trade-off. Of course, this is only the policy evaluation case, and what we'd really like to be able to do is not just get one policy, but be able to figure out what's the policy we want to deploy in the future. So how do we start to do this policy optimization? Well, I think in order to do this, we're going to need to not just take a max over all the existing policies, but to think about what their potential generalization might be. Now, the problem here is that we don't have very good error-bound analysis yet. There's been a number of different efforts, but I think we still have a lot of work to be done, which means we're in an exciting early stage. So in particular, important sampling estimators can leverage standard concentration inequalities, but they typically completely ignore the hypothesis class structure, meaning that we're ignoring whether the policy we're evaluating is based on linear regression or logistic regression or a deep neural network, and they tend to require a very large amount of data. There's other approaches that are based on things like kernel functions and averagers, but they tend to require an amount of samples that is exponential in the size of your feature space, which again isn't going to scale very well. And then there's been a lot of work thinking about bounds for function approximation for representing the Q function. You can think of this as also being related to things like DQN and an analysis for DQN. The challenge for this is that a lot of these ones depend on either assuming the domain is realizable, meaning that the function class you have really can represent your desired value function, or if it doesn't, it often requires an estimate of the true empirical inherent Bellman error, which you just can't know. And so that means that we can't evaluate these bounds. Like you can't actually compute what they are, which I think is a big problem if we want to use them for model selection. There's been some other really exciting work recently based on primal dual approaches, which have some of the same limitations. A lot of the existing analysis is dependent on quantities that we can't actually evaluate, which means that it's hard if we want to use these to compare across and actually make decisions about which policy we deploy. Okay, so maybe this is really hard. We would like to get here. We're not quite there yet. Maybe we can just change the goalpost. So I'm going to say instead of doing what we really want to do, maybe we can try to do something a little bit easier for a second, see if we make progress on that, and then go back. So instead of trying to find a generalization guarantee on the policy performance in general, I'm going to say we're only going to think about optimizing within a particular policy class. So someone gives you, say, a linear parameterized policy class. I'll give an example in a second. And what you want to do is compete with the best decision policy in that class. So there's some best policy in that class. You don't know what it is. And what you want to be able to do is say, compared to that best policy in the class, the policy that I select from that class is going to be close to that in a way that depends on the complexity of the class and how much data you have. So here we've got sort of a different alternative definition of complexity of the policy class compared to BC dimension, and then n here is the amount of data we have. And the nice thing is that we can basically do this. So we can answer this type of question and be able to give bounds on the performance we'll get of selecting within a restricted policy class for a particular type of decision making. So this is work that was led by Sheng-Kun Ni and with my colleague Stefan Wager. And these are really the first guarantees that I know of that allow us to say, by doing this sort of policy search method, we're going to be guaranteed to get the best possible in this class. So not just a local solution, but the best possible for a particular subset of policies. In particular, when to treat policies, which I'll talk about in a second. And actually, my student Yao Lu will talk about sort of a more generic class of policy search algorithms in the next talk. So in particular, when to treat policies are going to be a simplified decision-making setting where what we're trying to do is decide when to treat and what to do when we treat. So this is a slight expansion of optimal stopping problems, which include things like, when do you sell a stock or when to buy a ticket. Now we're going to allow ourselves to decide not only when to make a decision, but to allow not just binary decisions. So as an example, you can imagine you could track a whole bunch of state features of an HIV patient, and when a particular variable, say their CD4 count, drops below a certain threshold, then you decide to treat, and you continue to treat afterwards. So a linear thresholding policy would look something like that. Or for example, given a set of features, maybe time and health state, you could have a linear threshold policy that says when you reach a combination of this health state and this time period, you turn a treatment off. So we can handle not just linear threshold policies, but the idea is that we are generally going to think about things where at some point you get to make a decision, and you can do so given a set of parameters, and we want to learn what the best set of those parameters are. And of course, the key idea is, like, how do we do this search? How do we actually figure out what that policy is? And the key insight that we did here was we use an advantage decomposition. An advantage refers to what is the difference between taking this particular action versus, say, following a default policy or compared to an alternative action. And it turns out we can rewrite the difference between two value functions under different policies, as being a sum over advantages. This was done by Shyam Kakade and Susan Murphy a few years ago. And we're going to leverage this in the off policy setting. So in particular, in our case, an advantage is going to be the difference between if we treat now and make a certain decision, or if we wait one more time step and make a decision there. And the nice thing about doing this sort of decomposition is that now we sort of have a series of one time step problems, which means we can leverage a lot of the existing work in the treatment effect estimation community. In particular, it's been really exciting for me to collaborate with some people that come from more a statistician and econometrics training. And they have these nice ideas in terms of things like nuisance parameters, which are things like the Q function or the treatment probabilities, which you don't really care about. You care about being able to estimate the resulting value function or the performance gain. And so it's been very exciting to see some of those new types of statistical techniques. And in fact, recently at COLT, the Best Paper Award was given for a paper that was thinking about using those types of techniques more broadly. So in this case, one of the interesting things we can find is that even if you can only estimate some of these nuisance parameters, things like the probability of treating, quite inaccurately, like at fourth root rates, you can get rates in terms of how quickly we can estimate the best policy that are actually square root. So we looked at this empirically as well in a couple simulation domains. In particular, imagine that what you want to do is keep a health metric above 0, and this health state is sort of evolving over time with some Brownian notion. We're always going to start with the treatment on, and we're going to decide when to stop. And we're going to have a horizon of 10 time steps, and here we're going to consider linear decision rules. So in this case, what we want to do is compare between important sampling style techniques, our approach, which is ADR, and fitted Q. Fitted Q is really an extremely popular technique. It's closely related to DQN, which has been used extensively in some other deep reinforcement learning techniques. And what you can see here on the axes is that on the x-axis is the amount of data that we have, and on the y-axis is log of regret. Regret here is going to be the difference between the policy we would pick after that much data versus the real optimal policy in our policy set. And what you can see here is that initially, fitted Q iteration does quite well, but it starts to stabilize and it doesn't manage to continue to benefit from more data because at some point it's going to have a limited sort of function approximation ability, and so it may not be able to correctly model the data. On the other hand, our approach can continue to benefit from more data and continue to get more accurate estimates the more data that we have. But I think perhaps even more importantly than that, it provides a really nice way to have interpretability. So if we think about what these two policies are doing, in our case, we were thinking about having a linear threshold policy and searching over that parameterization, which means that we get a policy that looks like something on the left, where you can clearly see, with this type of state and this type of time step, we're going to continue to keep the treatment on, and at this point, we'd start to turn off the treatment. Fitted Q iteration is not searching over a parameterized policy class, and so you can get policies that look like the one on the right, where very small differences in the state, which is shown on the y-axis, can cause differences in the treatment decision. And I think that if we want these policies to be used by clinical decision makers or other experts who are not experts in our particular subfields, it can be really helpful to incorporate sort of interpretability aspects inside of the policies that we learn. And I think that's a big challenge with fitted Q iteration that these sort of structured policy search methods don't have. So in general, I think there's a huge amount of work to be done here. I think that we've made some exciting first progress in terms of trying to answer this question about how do we do batch policy optimization in a way that is rigorous and robust that we can deploy in the future. We've been thinking about all three aspects of this, and as I said, yeah, we'll talk about some other work on this shortly. But I also just want to highlight that there's many, many others that are thinking about this type of problems. And I think there's a huge amount of work to be done. In particular, everything that I've talked about today assumes no confounding. And meaning that the data that we have does not have any state variables that are being used to make decisions that we don't have access to. Now, of course, in many scenarios, that is not the case, particularly in observational health data. I will argue that I think even though the confounding problem is a very important one, there are cases where we can assume no confounding. In particular, in the cases of a lot of the historically studied RL cases, like Atari, like robotics, I think we mostly don't have confounding. And in those cases, these types of techniques that I propose could be used simply to get much better data efficiency than we've been able to achieve before. However, I also think that the no confounding issue is a really exciting one. It's something I'm working on, a number of other wonderful colleagues are working on. And I also think that other types of assumptions like no interference, assuming that treatment decisions don't spill over, are clearly false in many real-world domains. Things like if you do an intervention on Uber for Uber drivers, often Uber drivers will talk to each other, and so you can't assume that the treatment of interventions are not going to have any spillover effects. So I think there's a huge amount of technical questions to be tackled here. And personally, I think it's one of the most exciting areas. I think that often it's hard to find areas where there's both beautiful math and really important societal impact to be had. And I think that sort of counterfactual reasoning and batch reinforcement learning really exemplifies both of those. Now, despite the fact that, I've said there's a lot of really hard work to be done, we're only making sort of, we've made progress, but there's a huge frontier, so that you don't leave feeling totally depressed, I want to say that there's reason for hope, and I'll go back to the example that I said at the start, which is this case where we had about 11,000 learners' data of these trajectories, and we wanted to learn a policy that increased persistence. And what we did in this case is we did off-policy learning. And what we estimated is that the new policy would be about 30% better. So we expected that the policy we would deploy would do 30%, people would persist for 30% longer. And for those of you that deal with click-through rates, 30% would be an enormous gain. And so that's what we predicted. And so we ran another experiment with about 2,000 learners. And we did learn a policy that was 30% better. So I think that this was really exciting because this was somewhere where we really could accurately predict the amount of performance gain we got before we actually achieved it. And secondly, it illustrates how there is often an enormous amount of potential improvement to be had by using reinforcement learning and sort of off-policy sequential decision making in order to get to substantially better decision policies than we can currently achieve. So with that, I'll just summarize that I think that it's really exciting to think about, how do we make decisions in the world, how much data do we need to make those decisions, and how we can use those to tackle areas of real societal impact. Thanks.